So welcome back. This is our third video about the Jointree algorithm and also factor elimination. So in this video, let's talk about separators and clusters. These are two definitions that are going to be useful for us so we can have a more well-defined specification of the factor elimination algorithm. So a separator, it is defined over edges. So if I have one edge ij, I will define the separator for an elimination tree as a set of variables, and this set of variables are the intersection between the variables that occur in factors that are in one side of the edge and the other side of the edge. So let's take one example that's going to be easier to understand. Let's suppose that I want to compute this separator here. So in this figure is the same one that I have used in the previous videos, but now I have included the separators. And let's suppose that I'm interested in computing this separator here. So this separator will be the intersection between the variables that occur in factors in this side here and the factors that occur in this side here. If we look at this side, we know that we have variables a and b and variable a here, so it's going to be a and b, an intersection with whatever occurs here, and we have variable a, variable b, c, d, and e. So we have all variables here, a, b, c, d, and e. So it's going to be the intersection between these two sets here, and the intersection is the set ab. Exactly what is written here. And the separators are important because when you want to eliminate the variables during the factor elimination process, we want to know which variables we can eliminate, which ones we should maintain. And the variables in the separator are exactly the ones that we want to keep. All the other factors are not occurring in the other side of the edge, so we can eliminate those variables. So if we pre-compute the separators, it's going to be easier to specify the algorithm because we don't so far we haven't specified in the FEE2 algorithm that we need to eliminate every variables that occurs in the factor but is not occurring in the remaining of the elimination tree, and that is going to be an expensive thing to compute because we have to do a traversal in the elimination tree in order to figure out what are the variables that we have in the other factors. So if we pre-compute the separators, it's going to be easier. We just eliminate every variable that do not belong to the separator. Let's do another example just to be sure that we understood the idea of the separator. And let's suppose that we want to compute this separator here, right, over this edge. So it's going to be over this edge here. So in this side we have a, b. Now we have a, b. We also have c and d, c and d. So we have these four variables. It's going to be intersection with a, c, and e, a, c, and e. And that's going to be equal to going to be a and c. So going to be equal to a and c. That is exactly what is happening here. All right, so let's use the example that we have been using before and do a step-by-step example with separators and see how they can help us with the factor elimination algorithm. So this is the same example that we had before. We have this node here as being the root node. So I'm going to eliminate all the other nodes, and we'll keep this one. At the end, we'll have a marginal over A and C. And if you want to compute the probability of C, that was the task that was proposed before, we can finally eliminate the variable A. So let's check here if we understand what are the separators and where they came from. So we're going to start eliminating the node 2 here, and when we look at here, we see that this node has a factor over a and b, and a and b are occurring in the other side of the edge. So when I going through this edge here, I cannot eliminate the variables a and b, so I'm going to keep them. That's why the separator is over a and b. So the separator is telling us that we cannot remove any variable. So in other words, we are saying that we can eliminate any variable that are not a and b. But the factor is already over a and b, so it means that we cannot eliminate any variables. So we have this process here that we not eliminate any variables, and we're going to multiply by this factor here. So the new factor that are going to stay in this node here is going to be over a and b. So that's exactly what is being shown here in the right side. And now we're going to eliminate this node 1 here, and we need to compute the separator too. Let's take a look at the next slide. So now we have this factor to be eliminated, and it is over variables a and b, and variables a and b are also occurring here. So it means that the separator is over variables a and b too, so we cannot eliminate any variables. So basically what's going to happen is that the new factor here will have the multiplication of this guy here and this guy here, and it will be over variables a, b, c, and d. So we cannot eliminate any variables, and we're going to multiply by this factor, so the new factor will be over the 4 variables. And now we have this new guy here with the factors over a, b, c, and d. So now we're going to eliminate, I believe, the factor 4 and see what happens. Yeah, we're going to eliminate the factor 4. The factor 4 is here. It's over variables a, b, c, and d. And when we look at the other side of this edge here, we see that we have variables a and c and e. So we can eliminate all the variables that are not over A, C, and E. In this case here, we don't have E here, so we'll be able to eliminate the variables B and D. And we have to keep the variables A and C because they are happening here, and C is also happening here. So now we can eliminate the variables B and D. So just be attention that sometimes we confuse and think that the separator are the variables that we need to eliminate, but that's not true. What is true is that we should eliminate all the variables that are not part of the separator. So B and D are not part of the separator, so we can eliminate variables B and D, and the new factor will be multiplied here. And this new factor will be over variables A and C again. There is no problem here. So the next one that I'm going to eliminate is this guy here. Next slide. And that is the final step. So we have this factor here over C and E, and we have a factor over A and C, and the intersection will be C. And so we can eliminate the variable E, exactly what we are doing here, and this final factor here will be over A and C. So we have our final result. Now if you want to compute the probability of C, just for this marginal, we can eliminate A, summing out a variable A, and provide this result to the user. And this is the end of the simulation. So another important concept for the factor elimination algorithm is the idea of a cluster. And the cluster is also a set of variables, but in this case it's going to be the union between the variables that I have in a node I, that are the variables that we have in the factor associated with the node I, and the variables in the separators of the edges that connect to this node I. So let's take a look at one example that we have here. So these are the clusters, and this is the elimination tree and also the factors that we have with the separators here. So if you want to compute the clusters, what we're going to have to do is to look at what we have. For instance, for node 2, what we have in the factor, also in the separators that are connected to the separators of the edges that are connected to this node. So in this case, we have just this edge here, and this edge has a separator A and B, and the factor in node 2 has the variables AB. So the union is going to be AB, and that is the cluster associated with this node 2. For node 1, we have the variable a here in the factor and the variables ab and ab in the two separators that are connected to edges to node 1. So the union is going to be union of a, ab, and b is going to be ab. For this guy here, we have the factor with variables a, b, c, and d, and we have variables a and b here and a and c here. So it's going to be a, b, c, and d, and that's exactly what is written here. For this guy, I have AC, union with AC and C is going to be AC. And finally, for this guy here, we have CE, union with C is going to be just CE. And the clusters are important because we can figure out what's going to be the width of the elimination tree by the size of the largest clusters, largest cluster minus 1. So the largest cluster here is going to be this guy. So it has it have 4 variables and going to have a width equal 3. And you may ask yourself why it's 3 and not 4, because we have 4 variables here, and why we are defining as the largest cluster, the size of the largest cluster minus 1. And the explanation is that we need to make this definition compatible with the width of the elimination order. And you remember that when we defined the width of the elimination order, we said it would be the size of the largest factor that we build minus 1, because we are computing the width after the elimination of the variable, not before. So here is going to be the same thing. The size of the largest cluster will be the size of the largest factor, because we have this, for instance, we have this is the largest one. It is a cluster over A, B, C, and D. It means that we will build the factor over these 4 variables, but later on we will eliminate some of the variables when we eliminate this factor. So in order to make the 2 definitions compatible, we're going to say that's going to be the largest cluster minus 1. And you're going to see later on that we can convert, for instance, one elimination order into an elimination tree. So it's important to make those definitions compatible, because when we see those transformations, and when we see that those transformations are width preserving, so it will transform one thing into another and will preserve the width of the elimination order, for instance, into the joint tree. So the definitions will be compatible, so we have the same numbers between the 2 structures. So that's it. So let's take a look at the next slide. All right, so here we slightly modifying the elimination tree by changing one edge. So before we have this edge here, and now we have this edge here. And we saw that this elimination tree is a little bit more efficient than the previous one. And we can see that it has a width equal to, because the larger factors are these and these, they have size 3, minus 1 is going to be 2. Let's just double check here that these clusters are actually correct. So we have AB here with AB, so it's going to be a cluster over AB. They're going to be union the 2. And we have A here with AB and AB, so this is going to be a cluster AB. Here we have BC. We have ABC here and BC here, so it's going to be the union between these 2 sets. It's going to be BCD, that's correct. And here we have CE with C, the union is going to be CE. And here we have AC with union BC and C, so it's going to be AB, that's here, and C, ABC. So that is correct. So the width is 1 less. The previous, compared with the previous elimination tree, is going to be 1 less the width of that tree. And there are 2 key observations about clusters. The first one is that when we are about to eliminate one node I, the variables in that node are exactly the variables in the cluster I. So for instance, when we are about to eliminate this node here, we have the variables A and B in this node. And when we are about to eliminate this node here, we're going to have the variables B, C, and D in there. And that's an important observation, because when we think about the root node that will have our answer, that node will have the variables in the cluster associated to that node. So in this case here, when we look at this guy here, this node will have the marginal over A, B, and C, and we can use that node to answer queries about A, B, and C. So you may ask why we are talking about this, and just anticipating a little bit what's going to happen next. I'm going to use this idea of factor elimination and save the computations in each node. So instead of eliminating the factors, we're going to save that answers into the nodes. So each node will be able to answer questions about the variables in each cluster. So it's not going to happen now in this video, going to happen in another video that I'm going to see in the future. But we're going to see in the future that we're going to change the algorithm to the point that for instance, this node here will be able to answer queries about A and B. This also answer queries about A and B. This guy is going to answer queries about B, C, and D, and so on. For now, I'm going to just think about this special node R, the root node, and I'm going to think that this special node will be able to answer queries about A, B, and C. So now that we know clusters and separators, I'm going to rewrite our algorithm and use this notion, so it's going to be a little bit clearer to understand the algorithm. Let's do that in the next slide. So okay, we are now in the position to state the algorithm FE3. So FE3 is the same algorithm as FE2, but now we can use the idea of clusters and separators. So we have as input the network and the query variables Q, elimination 3, and also root node T, and the observation here that the variables that belong to the query must be a subset of the cluster that we have at node R. And I'm going to answer the prior marginal P of Q, and so we're still not dealing with evidence yet. So what we have here is, first, just to clarify, we have CI, that is the cluster at node I in the tree, and we have Sij, so there is a typo here, it should be Sij. It is the separator of the edge Ij in the tree. And the algorithm is basically the same thing. We're going to just make use of the idea of the cluster and separators. While we have the tree with more than one node, we iterated here. So the idea is that we're going to eliminate every possible factor, every possible node of the elimination tree, until I have just one node that's going to be the node R. So we remove one node I, so we need to choose one node that is not the root node, and it must have a single neighbor J in the tree, and we do the elimination process. Now we mention the separator Sij, and we're saying that this is a projection of phi I, and phi I is the factor associated with the node I over the separator Sij. So basically this, we haven't discussed this before, but this is going to be an annihilation of all the variables. We call that vars I, so all the variables that are in the node I, but Sij, right? And going to eliminate all those variables from phi I. And then you multiply this by phi j. This is the process of eliminating one factor, and this is going to be the new factor phi j. And we do this process until we have just one node, one factor, and at the end we project that factor over the variables in Q. So for instance, in our example in the previous slide, we have a factor that ended over for instance, A, B, and C, and if our query variables are just like A and B, we can eliminate the variable C here as a final step. Alright, so this is our factor elimination algorithm number 3. We're going to make now a break, and we're going to continue in the next video discussing the idea of message passing. And that will allow us to save the computations over all the clusters and answer queries over multiple clusters. So see you in the next video.